Hey, welcome back. As you can see, my Dbit grinder is in parts. It fell apart. So the story behind this is it's worn out. I went through it and it has some severe wear and needs some problems to be addressed. And while I'm at it, I'm also doing the Renzetti long travel modification of the main bar and some other minor things. So let's get to it. As you can see, it's already torn apart completely. The casting, there is nothing on it anymore. While we're at it, we might even paint it, because why not? So the main focus of wear is this thing here, the swivel. This sits here. The dividing head, the work head sits up here in this dovetail. And this is used to swing a 90-degree and also do radius grinding or ball grinding if you want to grind a ball shape, a spherical shape. And this has a lot of looseness in it. And this needs to be addressed. And also I want to improve the locking, because the locking tends to move this thing off axis, or not off axis, off position rotation wise, because it's just a pin pressing against something round. Not very elegant design. I replaced the main axis years ago against a hardened and ground piece of linear shafting. This is already very big improvement. But since I'm doing the Renzetti long travel modifications, which will increase the travel of this main rod from about 12 millimeters to something like 50 millimeters, this is not long enough, so I'm going to order a piece of precision round bar to make a new shaft. Also going to lap it like Robin. For most things you can just go and watch Robin's video. Also pulled the motor and the spindle. I pulled everything. Also we will do the main bearings, the sliding bearing in here where the main shaft can slide back and forth and rotate with Mowgli's. I have from another project some Mowgli's left, a lot left. This is a epoxy especially made for sliding surfaces. You can make bushings or flat sliding surfaces. You can make boxways. You can do a lot of things with it. It's great for building new machines, but also very good for rebuilding. It has severe limitations. It's relatively soft material. If you cannot take precautions so dust does not enter, you will get a problem, because this stuff will get chewed up by dust. I have the gutted casting only with the spindle and the main shaft here up on the surface plate with a piece of butcher's paper to not scratch the surface plate, because the underside of this casting is machined kind of rough. And I'm using my height gauge and the square and scale to get some dimensions. For one, the height of the main shaft to the lower surface here, to the surface plate, center distance, and then center to center distance of the main shaft to the spindle, and also the offset in depth. So for the height, I can just use the height gauge, drop the pointer on the shaft, zero out the height gauge, crank it up with the height gauge in, and repeat the measurement on top of the spindle. For the offset, the height gauge does not much help. I'm just putting a combination square up against the main shaft. Then I use a scale to measure off the largest diameter of the spindle against the blade of the combination square. These are not high precision measurements. This is just so I can put something into CAD, just to have a very raw blocked out model. So I went back through Robin's video of his Dbit grinder mod, and I took a careful look on his design, and I decided to change practically nothing because his design is already reduced to bare minimums and has brilliant simplicity. I'm doing exactly the same, elongating the main shaft here and increasing the travel to, in my case, almost 60 millimeters. This blue part here, this is the new screw. It has 2 axial needle roller bearings. Then we have a sleeve with the feed thread here and a relief in here. We have 2 ball bearings in here, which are preloaded against each other and bolted against the face of this main shaft here. And when you spin the threaded spindle here, the sleeve, which cannot rotate because there will be a set screw with a point counteracting its desire to rotate, this will move in and out and will give me about this much travel. And I figured it out so the main shaft here does not leave the bearing in its most extended position here. And back here it just runs up against this face of the screw, of the spindle. Out here will be the knob with the hand wheel, of course. And on this end, out here, where the shaft sticks out, we will have the Robin's design with the long momentum arm to provide the depth stop when grinding against the wheel. So let's make this main shaft and cast these borings with Mowgli's waylining epoxy. So I prepared the hardened and ground linear shafting. As Robin mentioned, this is basically a redo of Robin's video. The linear shaft is centerless ground, and centerless ground grinding leaves a lead spiral on the material, which is not ideal if we do the epoxy casting of the bearing fit. For that reason, I made a lap, which is just a piece of aluminium, bored to 25 millimeter with some saw slits on the circumference to give it space for the diamond slurry. Currently I'm running 3.5 micron diamond slurry. Later I will clean everything and run 1 micron for the mirror finish. So here we go. Let's continue with the lapping. Oh, and to make the lap extra simple, I'm just using a toolmaker clamp to put pressure on it. In an ideal world, this lap would have a little bit thicker walls to increase its ability to round up the work here. But feeling how the lap runs around the work, it should round up very nicely. It needs a little bit more drag. Yeah, like this. So let's take let's look at our progress here. And this looks already like a pretty good finish. Way better than the as-delivered centerless ground finish of this precision linear shafting. The linear shafting, the hardened linear shafting, is a nice basis as it's already hardened and relatively good ground. But after lapping it, this is getting ridiculous here. So I will clean everything, make sure I get all the diamond off, and then will take some measurements once it has cooled off. before I flip it around and do the other end that's currently in the chuck. And lapping is a horrendous mess, an abrasive mess. It's like some people, very abrasive. Okay, I'm done with lapping, and I hit it with some polishing compound on a piece of tissue paper. And as you can see, this is the centerless ground finish. It's good, but not, it's ground. But back here, we have a pretty decent finish. It's not the end all be all. Boing, and we just put a nice nick in it, but it's good. And we got the lead spiral from centerless grinding out of it, which is important. I got the linear shaft here all lapped and with a nice finish, and it's currently in the casting of the Dbit grinder. And here you can see the reason why I'm doing all of this. We have a solid 30 micron of play on this side. This side is better, but still with that much wiggle, you notice that when you grind very small tools, you get problems here. So that's the reason why we're doing this. To fix this, we're using Mogli's epoxy. This is a way-lining epoxy. This is normally used in building very large machine tools, but you can also use it to rebuild and build new machines. And what it is, it's used to cast sliding surfaces off a master. I used that on the lathe that I had before my Emco. I did all the bedways and the dovetails with it. And in this case, we're going to cut out material in here, treat the shaft with mold release, put it in, and then inject the Mogli's epoxy with a syringe. That's the plan, and then tomorrow we try to get this shaft out of here. Currently in these bushings there is no room for the epoxy. If this is the cross section of the casting, of the shaft running through here, center axis of rotation, there is no room for the epoxy to go. We could set this up on a milling machine, or in fact on the drill press in my case, and use a boring head to bore out these bushings to a larger diameter. But because these bushings or these cast bores, which are machined, are very close already, we can do something different. We can take a carbide burr in a die grinder, and we can just relieve the center section here. Just whittle away at the material and roughly remove it. The coarser the finish, the better, because the Mogli's epoxy has something to hold on to, some mechanical purchase. We just burr away the material, and we already have a hole in here for the oil port. We will tap that to an M8x1 fine thread for a circ fitting. And we will put the Mogli's in there until it pushes out the side, and then we'll proceed on from there. So first order is to burr out this material, but we absolutely leave a narrow band on both sides of the bore, same on the headstock side and on the support side, which, for one, it keeps the liquid Mogli's, which is very liquid, in until it's cured, and also it will center the shaft, so we do not have to take any additional precautions like an additional centering cone or ring to center the shaft. The bore that's already in there will do that for us. So that's a neat way to do it. Here you can see the bore as it's machined from factory with some nice scratches already in it. And now it's time to burr away most of the material in there. I have a what's that? A 6mm carbide burr with a 3mm shank in my NSK micromotor, and let's go. I think we'll take out about 0.5 to 1 millimeter in diameter. This is an extremely dusty operation. We removed a good chunk of material out of there, and when we put the shaft in now, hopefully don't scratch, you can see that there is a good amount of gap between the shaft and the bore. Or at least on the relieved part between the two bands of material that we left untouched. So that was on this side of the casting. Now we'll do the same in this bore, but without the camera, because it's already very bad accessible and the camera doesn't help at all. These are the holes for the oil ports. This is on the support end. And I want to use M8x1 screw and circ fittings like this. I used to have these oil points in here, but you like a flat surface to screw these up against. And this is a casting which has Bondo on it. So I'm taking a counterbore, a piloted counterbore that fits in here in my cordless drill, and I'm just going to put a very shallow counterbore on here. Just so this oil fitting has something to screw up against. Followed by a 7mm drill, which is the tap drill for a M8x1 tap. There we go. Countersink and M8x1 tap. There we go. That was harder than it looked. And when we take our M8x1 oil fitting here and screw it in, and this bolts nicely up against the flat surface of our counterbore. And then I can hit it with a regular grease gun. Probably filled with grease or with oil. I'm not sure yet what will be the better choice for this bearing. But considering it being in a grinding environment, oil would be nice because it flushes away everything that gets in. On the other hand, it's a very slow moving bearing, so a grease might be also an option. Not sure yet. I have everything prepared. The bores are cleaned with acetone. The shaft is coated with the mold release. Also, I have my circ fittings on the thread coated with mold release. I have the screw, which I will put in here, where the clamping screw goes, also coated with mold release. I already have 20 grams of Muglis in this cup. I have my hardener here, scale. I have a 7mm punch here that I will use. That's also the tap drill diameter of this hole. That I will use as a piston to extrude the Muglis out the bore into this cavity. I will put material in here before I put the shaft in, so I don't have to push as much with the piston. But that will be the final step. One last thing that I want to do, I want to hit the bores with a torch. this supposedly increases the holding power. This is like a poor man's plasma treatment. Okay, let's mix the Muglis. I already calculated that I need 3.66 grams of the hardener, which is reasonably toxic, so we're a little bit careful here. 3 point, yeah, a little bit over, but not crazy. Okay, this is how the stuff looks when you mix it, and as always with epoxy or with any two-component stuff that you mix it as long as you think you need to mix it, and then again as long. This stuff has a fairly long open time, so I think it's workable up to an hour. So I'm not in a crazy hurry here, apart from getting to bed because it's 22:43 right now. It's fairly dark outside. So, but that's a good time to do epoxy. Also, always scrape the walls and scrape the floor of your container. Reset your mixing stick and start over. Just do the good old epoxy meditation. Okay, this should be fine. Now we can line the bores with the epoxy. Just spread it out in there so we hit all the surfaces. The shelf life is exceeded probably, but since this is a personal project, nothing for a customer, and it still will harden. I don't worry too much about it being not as up to spec as it could be. Some people say this stuff is the devil's work in machine rebuilding. I kind of agree. If properly used, this stuff is awesome. But if not used properly, it's very tragic for machine tools. So let's get our shaft in here. So this used to slide in. And out the other end. There we go. That should do it. Yeah, you might notice with a little bit of expertise on the viewer side, you might notice that I'm anything but an expert on this stuff. I don't claim to be an expert in anything, but I'm absolutely not an expert at Muglising stuff. Now we take the 7mm punch, and we hope this works. Then we'll just use this to push down the Muglis into the cavity. And heck, this works. I let the Muglis run down the side of the bore so I don't trap a ton of air in there. Then we wipe off all the excess material and screw in the circ fitting and hope we can get it out tomorrow. Of course you use a new circ fitting if you do it, not one that's already contaminated with oil and what else. And if this didn't work, we can just tear out the Muglis with a scraper and a chisel and redo it. That's the nice thing about it. It's not like cast in there forever and eternity. So we take our circ fitting with the mold release on it. Oh, I hope this works. And bottom it out in the thread. This circ fitting will probably not work after this treatment, but only primarily after the threads, after a nice fit in there. Probably going to replace them with new ones again after we did this, but that's a minor issue here. So let's do the other bore. It's the next day. I flipped the casting around. The Muglease is now nice and hard. It's a relatively brittle material. Okay, I have a jack screw in here with a strap clamp as a backing plate, a long screw and a nut in here. Hex key out here, and I will get in with a wrench here and hold this nut still while I turn the hex key on the other end. And hopefully we don't break the casting. Okay, something gave. Getting a Muglease bushing out can be really nerve-wracking. Just whack the casting a little bit. This can lead to movement on our parts. I did some work to it. I drilled out the stuck oil fittings here. The mold release wax that I used was not enough to make them release on their own, so I had to extract them with a cordless drill and retap the holes. You saw me force out the main shaft. It was extremely tight in there. I cleaned up the bores, cleaned up the excess Muglease on the ends of the bores. Took some 3M lapping film, dusted off the surface of the Muglease just to clean it off, get rid of the mold release that's stuck on there. Drilled through the oil port, drilled the hole for the clamping screw, and used some oil, and I just worked the shaft back and forth and cleaned everything again, put everything back together with oil, and this is now what I have. This is moving relatively tight, very tight in fact, which is good. I will leave it like that. So, looking at an indicator held at the casting of the machine and resting at the main shaft here. It's in contact, and when I press the shaft up and down, yeah, I can get maybe half a division, which would be 5 micron. So I did some damage to it while hitting this outboard support. I preloaded this side with the screw, and I could see this outboard support bend. So I took a piece of wood and a hammer and I whacked it to break it loose. And in the process I chipped off some of the Bondo here, so we'll put some work into that. Here's a close-up of the Muglease bearing surface in there. As you can see, the surface finish is stellar. It's really good. I have one minor spot that it didn't get filled with the epoxy on the bearing on the other side on the 12 o'clock position, which is not a real big deal because most of the load is going down anyways, and there is still more than enough surface on a round bearing that supports it. I put everything together. I made some parts off camera because they're just turned parts with some threads and some ID turning. Nothing really crazy. And now we have some severe additional travel here. It's not ideal that the machine is sitting on top of a rolling cart at the moment, but I'll put it on a solid stand at some point. Let's make a mark here, whoop, and hand crank it to the extreme other end. It has 1 millimeter per revolution pitch. Okay, that's full travel. That's a solid 55 millimeters right here. And of course we have our rotation. And now we will take it apart and you will see the individual parts of it. So we have one screw, one axial screw here. That's for preloading the bearing. Would be nice if... So there's just a screw, M6 screw, and a hardened and ground washer, parallel ground washer in here. Then we have a set screw in here. Now we can pull this handle up. It has a recess bored into it. Then we have our first needle roller bearing, axial needle roller bearing. Then we have the original faceplate here, which we also will take off. And I decided to drop every single screw today. Twice, okay. This is the plate. It has the hardened washer in here. It has a bronze bushing in here. And then you try to remember which size of screw you had in there. Okay, it's an M5 screw in there. You unscrew it. Then you can pull this whole thing out of there. And so this long piece here is the nut, and this is the lead screw, which we unscrew now. This is the part you saw me threading. That's a very long screw. Both parts are made from 42 chromoly, pre-hardened steel, or commercial heat-treated steel. It's not really hardened. It's hardened and tempered. And we have an M5 screw in there. And you can see a ball bearing, and here is another ball bearing. And those two ball bearings are preloaded against each other with the screw, and there's still the spacer missing between the two bearings that sets the preload. But that's a simple piece, it's just a washer that's ground the thickness to set the correct preload. Different to Robin. Robin used a piece of the hardened linear shafting to make the nut, which is a very good idea. But he had issues with distortion once he cut the keyway into it, because when you cut through the hardened layer, the stress from hardening gets released, and this part will go egg-shaped quite a bit. So here we can see a second bearing. This piece was a little bit tricky to make, because we have an ID thread here, then we have a relief cut up to here, then we have a bearing seat in here, and a step, and it's bored for the other bearing from the other side. So the long boring was a bit problematic, but with the carbide shank boring bar, not impossible. Then we have a spacer here. And we have some long M4 screws. These screw into the original bolt pattern in the casting here. There we go. So that's all the parts for the long travel mod. These two are modified original parts. This and the spacer tube are the new parts. Apart from that, and the long or main shaft, there is nothing to it. It's really a relatively simple and very clever modification, which I can take absolutely no credit for. All that goes to Robin. But it's really a nice design. It's very simple. It works. It's with the hand crank with the tool. 2 axial needle bearings acts very nicely. It's really good. It's just perfect. It's the right amount of complexity and simplicity. Really neat. Let's do a dry assembly without the casting surrounding it, so you get an idea what I built here. So I have the nut with the 2 bearings in it. And we take a screw. The screw comes out the front. And the nut gets bolted to the main axis. And once I have the preload washer in there, I can just snug the screw up completely. In this case, I have to be a little bit careful so I don't crush the bearings. So these 2 parts are now mounted against each other. They can spin, but they are axially secured to each other without any play. We have our keyway here, and we have in the casting there is a set screw with a point, and which prevents the nut from rotating. Now we have our lead screw. Goes in here. I'm only going to screw it in a little bit because long thread. Normally we would have our spacer tube now, which I will leave off for sake of visibility. Then we have our bearing shield with one of the axial bearings going up against the shoulder, going in like this. Second axial bearing goes on the outside. Then our hand crank with an axial screw. Set the preload. And set screw from the side to prevent spinning on this thing. So now we have, so this is our bearing assembly for the hand crank. As you can see, spins, lead screw spins with the hand crank. Now imagine this nut here being stationary. Well, stationary in rotation, but it can't translate linearly. So when we spin the nut, it will move axially. And we can still rotate the main shaft like this for our main in-feed motion. That's the whole idea behind this setup. This is the lower base that clamps to the main axis, and I added the preload screw that Robin also has in here because the bore that goes through this part is a little bit on the big side, and to clamp it you have to exceed a lot of force on the clamping screw on the handle, and by preloading it with a screw from the back you transfer most of that load into that screw, and the clamping handle only needs a little bit of to finally clamp it. So here we go, adding a countersink. We're here at the drill press, not in the mill for a change. I'm using the power feed at 0.1mm feet per rev at fairly slow speed. This is the swivel arm, and it has an axis in it. I already removed the roll pin down here, and now I'm attempting to pull out the shaft from the casting. And this is in fairly hard. I put on 2 pieces of round stock with a hole in it, otherwise known as a pipe, some spacer, a washer, and the shaft is conveniently threaded, so I can just use a wrench to pull this whole mess apart. In a second, when I have the shaft out, you will see what I'm talking about at all. So this is in fairly tight. It's pressed in and secured with a cross pin. Okay, there we go. It's already loosening up. It's going easier. I think I'm going to redo this whole main shaft. Yeah, it's already coming out here. So need more spacer. We might be able to use a sliding hammer and pull it out that way, but if I have the option, I like to use something threaded to pull it out in a controlled manner instead of using a striking implement. Ugh. Okay, here we go. That's all the spaces. Those go back in scrap. Nut comes off. Washer, 2 keys. This is how all of this was together. Got the shaft out. It's just pressed in. We'll make this new because I don't like the way the clamping arrangement here works. There is a screw from the side that presses on this angled section with a tapered tip on the screw, and that just tends to gall up, and it's not a very elegant solution. We will find a better way to do it. Also, I want some kind of a bearing in here, an actual roller bearing. Probably a needle roller bearing. The next thing to address on this Dbit grinder is this motion here. This is the swivel motion used to grind radii and also to go from 90 to 0 degrees, or for angular settings when you grind a tapered tool, for example. Problem is, this is the shaft that rotates around, and this is just soft steel, and it's guided in this machined bore in the casting. More or less, it has significant side-to-side play. Too much for my taste. And also the clamping screw acts against this tapered surface here, which really doesn't work very well. So the original Deckel SO grinder doesn't have any bearings in it. It's basically built the same, but to a very high standard. The Deckel SOE, which is the improved and heavy-duty version of the SO, has radial needle bearings in it. What I want to do now is I want to put in 2 radial bearings, needle bearings, caged needle bearings. One here, one up here. I will put in an axial needle bearing up here to take axial load, and I will put in a smaller axial ball bearing down in here. There is already a cavity machined for this bearing, because I retrofitted this bearing in the past because the original solution with a washer running up against the casting didn't work very nicely. So that's already done. We need to fill this cavity up here, so this caged needle bearing has support, and also the washer of this bearing here has something to rest on against, otherwise it sits on thin air. On this part we need to remove this boss, cut it off, machine it down, and machine a cavity for this axial needle bearing. We can't recess the needle bearing in here very deep because we need the room. We need this caged bearing here very high up, otherwise the locking screw will hit the bearing cage, and that's not good. So I already have a slug of gray cast iron here. We'll machine a piece that fits in here, a little bit oversized, and glue it in with Loctite 648 bearing retaining glue. Then we put this on a machine, not sure yet. I'm probably going to mill it on using the boring head and do our final dimensioning to it. I made the filler piece from the chunk of gray cast iron. I have some Loctite 648 here, and we're going to stick it together. Good idea to clean the parts thoroughly. Loctite 648 is relatively tolerant to oil and things like that, but it's still a good idea to do as good of a job as we can. I machined the slug with a little bit of gap to give the glue some room to exist. And what I like to do, I put the glue seems like I need to buy a new bottle of lock. Well. What I like to do is to put the glue on the edge of the bore all the way around, and also wet most of the surface, and do the same on our slot that we're going to glue in. I pressed apart glued joints and notice that they tend, if you don't wet both surfaces, they tend to have dry spots that don't do anything for your glue bonding. But with some pre-wetting, like so, chances are pretty good. Give it a good spin so we spread the glue, and there we go. That's a decent Loctite joint, and I really should buy a bottle of Loctite. And in the meanwhile, we can take a look at this thing here. Make room for our needle bearing. I think we can do this on the lathe. And this will be rather entertaining to hold on to. But I have an idea. So here we are with sketchy setup of the month. I have a piece of 20-something millimeter round stock in the 6 jaw chuck, drilled and tapped an M6 hole into it. And this piece here already has a through hole from the past. I can also show a picture how I drilled that hole. It's drilled and reamed, it's precision fit. And I bolted this part just with one single screw up against this arbor. And then I indicated the bore and used the 6 jaw chuck with its adjustment here, with the 4 set screws, to get it reasonable true. Can't get it better than 20 to 30 micron, because the bore I'm indicating on in there is not exactly well machined. It has some roughness to it. So let's cut off this excess material, bore out the recess for the needle bearing, and proceed on. We're running at about 200 and something RPM, and I'm using the carbide shanked boring bar that I made in one of my previous videos. It's running very nicely. I bored it out to accept my axial needle bearing here, like this. And I made it so this washer here is proud of the surface. This will be recessed in the other part. So let's get these out. So let's tear this setup apart so you see how this is put together. But it's as simple as it looks. It's one screw. And this hole and this surface here were created in the same setup. So as you saw in the image that I showed, I clamped it with the shaft in place in the chuck and drilled and reamed this hole. This was for alignment purposes, but in this case it was very helpful for work holding, which is nice. So most major modifications to this part are done now. This angular slot here, this semicircular slot here, this is for the 90-degree swivel stop. There is a problem too. The stop pin works itself into the cast iron. Because cast iron is relatively soft, the pin is hard, and you're bumping into it all the time. So I'm considering putting a piece of carbide, tungsten carbide in there, which is relatively hard, to make a non-Brinellable end stop in there, but we'll see. I roughed out most of the central bore in the swivel base with a large end mill and finished it later with the boring head and a long boring bar. Then I used the auto-facing Woolhopter UPA boring head to cut the recess on top for the axial needle roller bearing. And misused the Woolhopter to fly cut the top of this piece in the same setup, so everything is true and parallel to each other. This is the new swivel shaft. It's made from an air hardening tool steel, and I'm using my small oxy-fuel rosebud torch to flame harden it. If this was a customer part, I would send it out for proper heat treat, but as this is a personal project, I'm not too worried about a super high-end heat treat, and the hardness test later will confirm what I did here. So cooling it down with compressed air to get it below the temperature where it changes its crystal structure, and letting it cool down. Here I'm using a 60-degree carbide cutter to recut the centers after hardening. I have a 60-degree point in the drill chuck and press the part up against the cutter in the lathe chuck. We're over at the surface grinder, and you just saw me grinding this end of the shaft. This is what runs in the needle roller bearings. This end goes into the axial ball bearing, and this end will be a semi-press fit into the swivel arm of the Dbit grinder. And this is just a clearance shoulder here. And as usual, grinding on the surface grinder, round parts on the surface grinder works extremely well. It's so easy to control size, cylindricity, diameter end to end. To change diameter end to end, you just tilt this whole setup tiny amounts by knocking it with a copper drift around. It's just a beautiful setup. And now on the new grinder with the DRO, it's a drunk person could grind really nice. This is 123/63 tool steel, otherwise known in the ANSI world as A2, air hardening tool steel. You saw me torch hardening it and then giving an air blast with the air gun to cool it down. And when you do torch hardening, you need to leave quite a bit of allowance because you decarburize the outer layer, and that will never get hard. So I left on 0.5 millimeter in diameter. I took a reading on the hardness tester after hardening, and it came out at something like 40 Rockwell C, which is not much. I ground off 0.2 millimeter in diameter, I think, or 0.25, something like that. Then I did again a hardness test, and I'll show the picture here. It's 62 Rockwell C. That's a nice hardness for a shaft that runs directly on roller bearing elements. So let's grind this diameter. We will touch off on the shoulder, move in a tiny bit, and then we will plunge down to final diameter. Well, we will plunge down, move out, measure, adjust RDRO, because I dressed the wheel. I needed to dress the wheel after grinding all this diameter here. So let's go. Here's the swivel arm, and here's the part we just ground, and that's a nice nice sliding fit there. Semi-press fit, I would say, or very light press fit. You might notice that I didn't use the huge centers that I put in there because the centers in my cylindrical grinding jig are too small. So I put in some M6 screws, faced them off in the lathe, and center drilled those. That way I have nice and small centers in this part, and I can just remove the screws, and I have the M6 threads beneath it that I need for assembling this thing. To bring this video to an end, it's not completed yet, this mod. There was a lot of more work to do, but I can do a first basic assembly. We have our swivel arm and the shaft we just ground, our hardened shaft. It's a nice tight fit in here, and it gets screwed in from this side. I will countersink this and put in a countersunk screw because the socket head is in the way of the grinding wheel. But now for test assembly, this is fine. This pulls the shaft up against the shoulder. Shoulder is squared up with the grinding wheel to the diameter we ground. This inner surface, this outer surface, and the vertical wall here are all done in one setup on the lathe. So these are running true to each other. All very nice. Now we add our hardened washer for the roller bearing, axle roller bearing. I'm assembling this without grease or lubricant because I'm going to tear this down again about 1,000 times until I got everything right, and I don't want grease everywhere because it will collect dust and stuff like that. Not ideal, but for a test assembly it's fine. Add our needle cage. This is the lower swivel. I already have the 2 caged radial needle bearings in here. Down here is the second one up here, and I glued in the hardened washer with Loctite 326. This drops over here over the hardened shaft with the needle bearings. There we go. And we add our axial bearing down here, a washer and a screw. This is not the final design. The final design of this washer will be in a way so. First of all, it covers the gap down here so no dust can enter, and also it will have a shoulder that I can grind down to set the preload of the axial bearing. Right now I'm just adjusting it by feel. Oh yeah, there we go. Oh yeah. Oh yeah, oh, this feels excellent. Has a little bit of preload. It's not moving by its own. Well, it's almost. You can. It has a little bit of preload. It feels very firm and very stiff, and it probably is because of the huge axial needle bearing in there. We have barely a gap here. 50 micron feeler gauge, and this barely fits in the gap between those two parts. So that's a good baseline for dust protection. Our clamping screw can still go in here, but we will make it in a way so it doesn't damage the shaft because the original design here is rather stupid. So yeah, this is so far very much of a success. I'm really happy. The only oopsie that happened is when I bored this long board to 20 millimeters for the needle bearings, I broke through here. This is not too bad. I'm going to cut a piece of cast iron that fits in here, glue it in with the Loctite 326, reopen this bore, and no one will ever know. There is still more than enough material surrounding this clamping bore, so this is not an issue. I put the assembly in the benchwise, and I have the upper part here free to swing, and I have an indicator here on the back of the vise with an indicator against the upper swivel arm, and I have my high spot here, and now we can check for side play. When I press against this part, it always goes back to 0 without any hysteresis. Apart from me swinging it side to side, then of course my 0 or 40 changes. But this is brilliant. This is really, really nice. I'm pleased. This is about 1,000,000 times better than before. I can't wait to grind a nice radii on a Dbit. RAL 6011. Perfect machine color. So, thank you all for watching. I'll be back.